All right, I think we'll get going. Thanks everyone for attending our webinar today titled Beyond Bankability and Risk, How to Maximize Module Financial Value. We have two speakers today, Tarn and myself.
Hi, I'm Tarn Yates. I work as part of the Anza tech team. Been in solar now for about 16 years. And over that period of time, had roles focused on design, cost estimating, performance modeling, as well as financial analysis.
Thanks, Tarn. And Tarn is on the tech team at Anza today. And I am Aaron Hall. I am the president and co-founder of Borrego. I have been in the procurement of module space ever since I started 21 years ago. And I'm an executive of the Anza business, and I am happy to share some of the insights we've learned over the years with you folks today. So first, I want to just cover the context, what part of the procurement process we are and are not talking about today. And then we're going to get into the financial analysis calculations and the metrics that are used to perform those. Then we're going to talk about the levers that can be used to optimize those metrics. And then we're going to take it home with going through two case study examples to put some numbers to the theory and the discussion and the concepts. And then we are going to leave time for questions at the end, probably about 15 minutes. So feel free to enter your questions using the chat function at the bottom of your screen. If it makes sense, we may stop and answer questions during the presentation. Otherwise, we'll just address them all as much as we can get to at the end. So the supply chain is volatile, as we all know, and the supply is constrained. At least that's the market we find ourselves in today. And the challenge is looking for available modules that are competitively priced, available when you want them. There are a bunch of questions to answer along the way to mitigate risk and to make a sound decision. Module availability, pricing, or other information is constantly changing, and new information or diligence can send you back to the beginning of the game. And you can see we have this kind of a metaphor of game of chutes and ladders. We wrote a blog post on the topic that you can check out on our site at anzarenewables.com, and we'll continue to add to that blog post. So to be clear, what we're focusing on in this webinar is the part of the game, if you will, once you've answered all the other questions you need for project fit and de-risking, where you evaluate the financial value of your various module options. What are the financial calculations that are best to do, and what are the levers to increase your financial return when selecting modules? We're not covering a lot of the process and procurement. Data collection, the PAN files, the data sheets, the install manuals, etc. Understanding that data and filtering it, diligencing it, etc. We're not talking about risk mitigation and UFLPA and contract terms for counterparty risk or any of that today. We're just talking about the financial calculation piece of it. So today, as I mentioned, we're going to go through two case studies, one 49 megawatt utility scale tracker and one 5 megawatt DG fixed tilt system. What you're going to see, what you do see here is a redacted screenshot from our Anza app online, where we provide you your list of project-specific module options, and we rank them by net present value, highest to lowest. In one of the case studies, you're going to see the most net present value was not the lowest cost module, whereas the other one it was. And you're also going to see in one case study where the large format module, in this case, the 650 watt module, is a better choice. And you're going to see where it's a worse choice. And we're going to dig into why in both examples. Let's begin understanding the cash flow, a basic cash flow, before we get into the levers. So first of all, there's obviously outgoing and incoming cash. So for the outgoing cash, we have a year zero cash out that is represented by the capital expense, sometimes referred to as CapEx. And then we have the ongoing over time, life of the project. We're going to talk in 20-year life today. You have those expenses that you're going to accrue over time, and those are referred to as operating expenses or OpEx. And then we have the incoming cash, which we refer to as a revenue, and that's over the life of the asset, or we're going to talk about today, 20 years. Those annual cash flows get totaled and discounted to arrive at internal rate of return, or another metric that's used as net present value. At Anza, we focus on net present value, and that's the metric we're going to be referring to today in our examples. Just unpacking those a little further is the capital expense includes things like the module cost itself, the balance of system costs, such as racking, inverters, transformers, and wiring, as well as labor. And then, of course, any fees required to acquire the asset in the first place. Under the cash over time going out column category of OpEx, we have O&M preventative and reactive maintenance, ancillary services such as vegetation, clearing, and washing, taxes, and the lease payments for the land. And then lastly, on the cash coming in, the revenue, that's mostly comprised of the energy revenues, which is the production of the system multiplied by the value of that energy, or often the PPA rate, as well as the incentives from taxes, like the tax credit, depreciation, etc. I will note that production degrades over time, and that's something that's very important to keep in mind when performing the analysis. All right, so IRR and NPV take into account the lifetime of costs and revenue streams, and it is more appropriate than a simple one-year analysis that, if done, may lead you to purchase simply based on the module price itself. That is going to leave a ton of value on the table. We've seen that time and time again. So I'm now going to hand it over to Tarn, who will be diving into the levers that impact this cash flow and therefore the net present value of projects.
All right, thanks, Aaron. So what I'd like to do is give an overview of how a different module selection can have an impact on a project. I'm going to start by talking about the BOS impacts, the balance of system impacts that module selection can have, and then I'm going to talk about the revenue impacts. So starting with BOS impacts. At this point, I'd say even more than just a few years ago, modules are being produced in a variety of form factors, wattage ratings, and cell configurations. And these different configurations, these different characteristics do have an impact on how much it costs to build a project with these different modules. So let's dig into this a little bit. First place that the module selection can have an impact is in the module installation labor. The cost of this can be estimated in a number of ways. It can be dollar per watt, it can be dollar per module. But really the best way to estimate it is it's going to take a certain amount of time to install each module. That time is based on what racking product you're using, and then also based on the physical size of the module. You take that time, multiply it by a wage rate, you have your module installation costs. At this point, most of the modules on the market are so large that they do take 2 people to install. So what that means is that while larger modules do take slightly more time to install, it's not by a lot. And so there really is a direct relationship between the total quantity of modules that you have to install for a project and the installation cost. The next place that module selection has an impact is on the racking and foundation costs. For both single axis tracker projects and fixed tilt projects, really what you're trying to do to minimize the racking and foundation costs, you're trying to maximize the number of watts, either per track or row, or per table, and also per foundation. As I mentioned at this point, there are a wide variety of module form factors, different lengths, different widths. These different form factors, when combined with the physical limitations of the racking product, they'll have a maximum track or row length or a maximum table area. So when you take these different physical module sizes, have them work with the limitations of the racking product, you can see a large difference in the number of watts that you can get per row or per rack or per foundation. In the last place that module selection has a real significant impact is in the DC source circuit material and labor costs. Again, over the last couple of years, module manufacturers have started using different cell sizes and different wiring strategies that end up producing different open circuit voltages for the modules. And really what the strategy there is to produce a lower open circuit voltage because that increases the number of modules that you can have per string. And what we see with these lower open circuit voltages is it does allow for string lengths that can be 10 to 20% more modules per string. This does reduce the total number of strings required for a project, and therefore just reduces the total feet of wire that you have to install on site. All right, moving on to performance or to revenue. So the revenue that's produced by a project is it's based on the energy production of the modules. And each module has unique performance characteristics. Some of them perform better in high temperatures. Others reflect less light off their surface or have fewer losses due to light-induced degradation. These individual performance characteristics are captured in the PAN files that we use when we run energy simulations.
Tarn, real quick, what are your thoughts on using manufacturers' internally generated PAN files?
Yeah, so when we run our analysis, we don't use PAN files directly from a manufacturer. Whenever possible, we use PAN files that are based on third-party test data. And we have a series of criteria that the third-party testing has to meet. It has to do with the number of modules that were tested and what procedures or protocols were used to produce the test data. And not every third-party PAN file that we receive meets our standards. We do sometimes end up rejecting third-party PAN files. But again, so our preference is to use the third-party PAN files. When modules are new, when they're brand new, there hasn't always been the opportunity to do that third-party testing. And so in that case, we are left using the manufacturer's PAN files. But before we will use those files, what we do is we'll run performance models with the manufacturer's PAN files, and we will compare the results to all of the other modules that are in our database. What we're doing there is making sure that their performance fits within a reasonable or expected range. And then usually manufacturers' PAN files do include an IAM profile, but they often don't include LID losses. And we have our own somewhat slightly conservative default values that we use in place of what the manufacturer provides for both IAM and for LID.
Is it safe to say that what you described is largely what an independent engineer might do?
Yeah, really, I was talking about the procedures and protocols that we, or the criteria that we have for accepting a PAN file. What those are based on is many years of our interactions with IEs and really understanding what they are looking for and what they would accept. All right, a few more things here on the revenue side. In addition to the performance characteristics that are captured in the PAM file, different modules will have different degradation rates. Right now, it's most common to see rates of either 0.5 or 0.45%. But those degradation rates can have a real impact on the revenue over the life of the project. And then the last point here is ground coverage ratio and shade losses. At this point, we don't see much differentiation here. Most of the modules that are on the market have efficiencies that are pretty tightly clustered. They have very similar efficiencies. If a module did have a higher efficiency, it would allow for a lower ground coverage ratio. It would allow you to space the rows further apart, and you could have fewer losses. We are expecting over the next couple of years, as TopCon modules or heterojunction modules become more common, we might start to see more differentiation in this area. All right. So now we're going to dig into the case studies and the details. So at the start, Aaron showed an example of a 49 megawatt single axis tracker system. And what we said was that choosing a less expensive 540 watt module over a more expensive 650 watt module would, can we go to the next slide? All right, so choosing the less expensive 540 over a more expensive 650 would leave almost $600,000 on the table. So I want to dig into the details of this analysis and show how we came to that conclusion. And where I'd like to start is looking at the column that's on the far right of this slide. It's the one that says CapEx savings. Go to the next slide. Okay, so what does CapEx savings represent? This is the delta in the all-in cost to build the project. It includes not only the module costs, but all of the other components required to build the system. So it includes racking, DC wiring, inverters, fencing, everything else required for the project. And in this case, when you see a positive number in that CapEx savings column, what it means is that a project built using the 540 watt module will cost about $300,000 less than one built with the 650 watt module. Now let's look at this number a little more closely. And what you see is the delta in the module price between the 650 and the 540 is 4.3 cents. But when we look over at that CapEx savings number, $293,000 for a 49 megawatt system is only 0.6 cents. So there's only a 0.6 cent delta in the cost to build with these two different modules. And so why is that? The reason is that there's a BOS pickup for the 650 watt module of 3.7 cents. And because of that, the all-in CapEx cost between these two options actually ends up being fairly close. So now let's walk through, okay, 3.7 cent pickup to the 650, where is that coming from? How do we get to that number? So the first part of this is in the module installation costs, and this is, again, fairly straightforward. There are over 15,000 fewer modules to install with the 650s compared to the 540s. And that leads to a small pickup of 0.3 cents in module installation costs. All right, the next thing to talk about is how these two modules impact the racking and the foundation costs. So as I mentioned a little bit earlier, the goal is to maximize the number of watts that you can get per tracker row. And when you're trying to do that, there's two constraints to think about. The first one is the maximum length, maximum physical length of a tracker row. Each manufacturer will have a limitation on the physical row length. It could be 122 meters, for example. So that's one constraint. The other constraint is the number of modules per string that you can use. It's best practice to fit a whole number of strings per tracker row. So you want 3 strings or 4 strings per tracker row. Okay, so those are the two numbers we're working with. Maximum physical length of the tracker row, number of modules per string. So, whoops, go back. So looking at the details here, what you can see is that the 650 watt module has a lower voltage than the 540 watt module. And what that means is that for this location, the 650 watt module can string in up to 30 modules per string, whereas the 540 has a maximum of 27 modules per string. Also, based on temperature conditions and the inverter that's being used, there's going to be a minimum string length, and we have those listed here as well. All right, so now the question is, what combination of modules per string and number of strings maximizes the number of modules that you get per row? In this particular case, the way the numbers work out is that the best utilization of a tracker row with the 650 watt modules is to use 3 strings of 30, which gets you 90 modules per tracker row. And then with the 540 watt module, the best configuration is 4 strings of 25, which gets you 100 modules per row. And just a little side note here. So I was reviewing these numbers with our racking expert in preparation for this webinar. And when he first started to look at these numbers, he was surprised to see that we were only fitting 100 modules per row with the 540. His expectation was that we'd be able to fit a few more than that. But when he looked at the details, what he saw is that the 540 watt module actually has a 30 millimeter frame. And so for this particular racking product, when snow load gets to a certain level, and if you're using a module with a 30 millimeter frame, you actually have to allow for what are called post gaps, which are empty spaces over some of the foundations. And so those post gaps effectively limit the length of the tracker row that you can utilize for installing modules. And it turned out that 100 modules is correct in this case.
Yeah,
okay.
Quick question, Tarn. You
Sure.
mentioned best practice is not splitting up a string, going from, or having only whole strings on tracker rows. Is that really a non-starter to jump from one string to another across tracker rows?
Sure. So we've asked ourselves that question a number of times. We've, often thought, hey, maybe we should try to squeeze a few more modules per row, run jumpers from row to row. And every time that we've run the analysis, we've found that it's more cost effective to keep a whole number of strings per row and to avoid running jumpers.
Thanks.
Yep. Okay. Right, so we got 90 modules per row with the 650, 100 modules per row with the 540. You will see we have fewer modules per row with the 650, but because it's a larger format module, we're actually getting more watts per row with the 650. So we get 58.5 kilowatts per row with the 650. We only get 54 kilowatts per row with the 540. Result is with the 650, we need fewer total rows and we need fewer total foundations. And what we see is a pickup of 2.1 cents in racking and foundation costs for the 650 in this example. All right, next we're going to move on to DC wiring. All right, so this is the last place that we see significant pickups for the 650. And this goes back to what I was talking about on the slide before, which is the lower voltage of the 650 watt module. That lower voltage is allowing for strings of up to 30 modules, whereas with the 540, having both to do with the voltage, but also the best configuration with the tracker. For the 540, we're only using strings of 25. So the result here is 1,100 fewer strings with the 650 and over 300,000 feet less wiring that has to be run on site. And so what we see is a pickup of 1.3 cents for the 650 watt module in DC wiring costs.
And does the DC wiring category include things like module connectors and zip ties?
Yeah, very, very good point. Yes, that pickup does include that. Yeah, every module is going to need wire management. Very often it's zip ties, and every module is another connection that has to be made. So just looking at the module quantity, you can see that there's many fewer modules with the 650, and so there's savings in the wire management and connections, and that is included in that cost. All right. So we stepped through the CapEx savings and showed where the pickups were coming from for the 650 watt module in terms of BOS costs. But coming back to these numbers that we had up here before, what we see is that the 540 watt module still does have a slight edge in terms of CapEx cost. But what we haven't looked at yet is the revenue. And this is what flips the best choice module in this case from the 540 over to the 650. What we see when we run revenue calculations is that the 540 watt module will actually produce almost $900,000 less in revenue than the 650. And so why is that? Next slide. Okay, so it has to do with the calculated energy production of each module. As I mentioned earlier, each module has their own unique performance characteristics, and those characteristics are captured in the PAN files that we use to run the performance models. And what we see when we run models for this project is that the yield or the production of the 650 watt module is actually 2% higher than the yield for the 540 watt module. There's a variety of reasons for this. You can see them listed in the table here, but let me highlight two interesting points. First is that the largest delta here is in IAM losses, and those are the losses that are related to how much light is reflected off the surface of the module at different incident angles. The graph on the right here shows the IAM profile of the two modules, and the 650 watt module is in blue and the 540 watt module is in red. And what you can see is that the amount of light that's transmitted through the glass at large incident angles remains higher for the 650 watt module than for the 540 watt. The other loss here I wanted to point out was the one at the bottom. It says inverter loss over nominal power, which is another way of saying clipping losses. For this design and in this location, and because the 650 watt module is a higher performer, it's also seeing higher clipping losses, which actually acts to decrease the yield delta between these two modules. In a different location, or if the DC to AC ratio was less, the production delta between these two modules could be even larger than what's shown here.
Tarn, is there any other elements of the revenue delta that you didn't capture here in the summary?
So there's definitely potential. There could be. In this case, the other thing that I haven't mentioned is degradation. In this particular case, both of these modules do have the same degradation rate, so that's not coming into play here. But I ran a calculation on this project looking at the difference between a 0.5% and a 0.45% degradation rate. And what I saw was that just that small difference would have an impact of about $165,000 in the revenue over the life of the project.
Or is it the revenue or the net present value impact?
That's the revenue impact.
Okay.
So you're right. The NPV impact would be slightly different than that. All right. Let's move on to the next slide. Okay, so we've run through that example, and just to summarize, what we saw is that a 650 watt module that costs 4.3 cents more than a 540 watt module was the correct choice. So 650 was the correct choice on this single axis 50 megawatt project. And the reason for this was that first there was a BOS pickup for the 650 watt module that brought the all-in CapEx cost of the two options down to a delta of just 0.6 cents. And then there was a 2% pickup in yield for the 650 watt module, which resulted in an increase of almost $900,000 in revenue.
Of net present value from the revenue, right?
Well, it was a $900,000 increase in revenue. When you combine those two things, what you see is an NPV delta of almost $600,000 between the two options. Okay, so 650 watt module was the best option in this case. And we're all busy. We're all looking for ways to save time. And based on this example, you might be tempted to walk away with a rule of thumb that you can pay at least 4.3 cents more for a 650 watt module than for a 540 watt module. What we'd like to do next is run through another example, which is going to show you that that wouldn't be a good rule of thumb to walk away with. And this next example is going to be a smaller fixed tilt example. Go ahead and go on to the next slide. I do want to call out right at the start here, we are again comparing a 540 watt module to a 650 watt module. But these are actually two different modules than we used in the first example. All right, so for this example, again, 5 megawatt fixed tilt project, you're better off using the 540 watt module. And if you were to have, based on that previous example, said, oh, I'm going to use a 650 in this case, you'd actually be leaving almost $150,000 on the table going with that 650 watt module. To dig into this, let's start again by looking at the CapEx side of things, which again, just a reminder, it's both module cost and BOS cost.
Also, just to point out, this is a smaller project, so 150,000 is a bigger deal in terms of cents per watt. We're talking about almost 3 cents.
Yeah, yeah. We go to the next slide. Yeah. So in this example, the price delta between the two modules is very similar. It's actually just slightly less than it was in the previous example. And if you remember from the previous example, the CapEx delta came down to only 0.6 cents. But what we're seeing here, what Aaron was just pointing out, is that we're seeing a CapEx delta of 3.1 cents. So what that means is that while we do see a BOS pickup for the 650 watt module in this example, it's not nearly as large. It's only 1.1 cents versus the 3.7 cent pickup we saw last time. So again, let's dig into the details of where that's coming from. Next slide. Yep. So the first place is module install, and this is very similar to what we saw in the previous example. There are, again, many fewer 650 watt modules to install. And so we do see a pickup for the 650s of 0.2 cents in module installation costs. Let's go to the next slide. So the racking and foundation costs is where we see a big difference. This particular project uses a fixed tilt rack that is made up of discrete tables rather than a continuous row. And based on the wind and snow load conditions for the site, this table will have a maximum physical area. So similar to trackers, but without having to worry about a whole number of strings, the goal is to maximize the number of watts that you can fit per table. You know, that's in order to minimize the cost of the racking. You're trying to get as many watts as possible per rack. So for this particular project with the 650s, the largest rack you can use is a 2x9 setup, which gets you 18 modules per table. Then with the 540s, the best configuration is 2x11, which gets you 22 modules per table. The result here is you end up with slightly more watts per table with the 540 watt module than you do with the 650. And so you need, again, slightly fewer tables and slightly fewer foundations. You really could almost, we call this a wash almost, but when you run numbers on it, it's a 0.1 cent pickup for the 540s in the racking and foundation costs. All right, going on to—
Oh, before you move on, just a quick question. Will the 540 form factor always have lower racking and foundation costs on fixed tilt projects?
No, so that won't be the case. There's the dynamic that's at play here can switch back and forth depending on the snow and wind loads. I did, again, looked at another example for this one with even higher snow loads. And in that case, you could fit slightly more watts per table with the 650 than you could with the 540. So no, it can switch back and forth depending on the project and depending on the form factor of the modules as well. All right, so DC wiring. Again, these are different modules than the first example. If you look closely at the VOC of the 650, you'll see it's a little higher than what we had in the first example. For this particular project, the 650 is constraining in 29 versus only 27 for the 540s. Again, result of this, many fewer strings and much less string wiring that needs to be run for the project. So for the DC wiring cost, we see a pickup of a penny for the 650. Okay, so we walked through the BOS breakdown, and what we see in this case is that there's a 1.1 cent pickup for the 650 watt module over the 540 in terms of BOS costs. And this is a smaller pickup than we saw in the previous example. But thinking back to that previous example, what we did see there was that the 650 watt module had a significant increase in revenue. over the 540 watt module. And so you might be thinking, okay, well, we'll see that same delta in revenue here. But when we look at these numbers, if you look at the revenue delta column, you'll see that there's almost $8,000 delta. That's not a very large number. That's a pretty small difference in the revenue for this project. And so let's look at the details of why that is.
Hey, before we do that, I just want to ask a clarifying question I asked before, but I'm not sure I got my head wrapped around their answer. When you say revenue delta, in this case 7822, is that the actual revenue delta over 20 years, or is that the present value impact, net present value impact of a revenue delta that's like $10,000? You know what I mean?
Got you. I get what you're saying. The number that we list here is the discounted delta. So it is the net present value of the delta.
It's clear to me now. Cool.
Okay. Yeah. Okay, so let's look at the performance characteristics of these two modules. When we run performance models, what we see is that in this case, the 650 watt module only has a 0.1% higher yield than the 540 watt module. But it's not the case that these two modules have identical performance. If you look at the graph on the right here, what you'll see is a comparison of the irradiance and temperature losses for the two modules, as well as a number of other modules that are in our database. And what you can see is that the 650 watt module actually has about 0.6% lower losses. So that means better performance, but lower losses than the 540 watt module. But the 650 watt module has higher losses in other areas. And in the end, these net out to only a 0.1% pickup in performance for the 650 watt module. In this example, the modules again have the same degradation rate. And so that's again not coming into play in a revenue delta. All right, so where does that leave us on this project? Let's go next slide. So again, on the CapEx savings side, we saw a smaller pickup of only 1.1 cents for the 650 watt module over the 540. So we are seeing what are significant CapEx savings for the 540 watt module in this case. And we saw a very limited revenue delta between the two modules. And so in this particular example, the 540 watt module ends up being the better option. All right, with that, I'm going to hand it back to Aaron.
Great, thanks, Tarn. So yeah, next slide. I'm just going to summarize some of the takeaways for the audience today. First, one of the takeaways is that, lowest cost module does not always entail highest value. In fact, we've seen, and here we've seen some examples that where you can have a delta in module cost of 4 or 5, I think I might have seen some examples of 6 cents per watt, be overcompensated or balanced out by those other impacts, such that the value was still better using that 6 cent higher cost module. So cost and value do not correspond to each other and follow a linear curve by any means. Next takeaway is large modules sometimes are better than smaller format modules in terms of even just simply looking at BOS cost impacts or overall and counting both the CapEx and revenue, and therefore the present value delta. But that doesn't always hold true, and it's highly variable based on the project specifics and wind and snow loads and the rack you're using, et cetera. So the point is that projects are complex, and a specific analysis is critical in order to arrive at the right answer. Right answer being the one that will yield the highest value or highest net present value. So one procurement professional might be tempted to spend all of the time, run all the traps on analyzing a specific project, coming up with a confident determination that, okay, this module is definitely, let's say this 650 is definitely the right module for my project. And in this case, I'm saving, X cents per watt as a result of CapEx and Y cents per watt as a result of revenue. And so then on the next project, I don't have to do all of that analysis again. I'll just port over the rules of thumb I got from the last project. And what we hope to have demonstrated today is that that's a fool's errand. And you're going to often leave a ton of money on the table and make an inaccurate determination based on those rules of thumb that are really project specific. Next slide, please. This is our last slide before questions. Borrego has over a 20-year track record as a leading developer and EPC in DG and utility scale solar. We're excited to enable the rest of the industry to take advantage of the IP, the relationships, and the scale that we bring to the Anza marketplace. We saw over and over again how choosing the right module could unleash 6 and 7 figures of additional value, even on a small or medium-sized DG project. In this example today, we saw, I think it was a 3-cent delta. Now, all of our customers can optimize their projects in a pretty much seamless way. Our customers submit projects on our platform, and they receive an NPV ranking table showing them all of the modules that are available for their project schedule, with prices delivered to site ranked in order of highest to lowest NPV. At Anza, we buy at the gigawatt scale and have 25 negotiated and executed supply purchase agreements that enable our customers to tap into available capacity within minutes of identifying the best option. There's a lot of nuance and a lot of data analysis required to come up with the optimal choice, as you can see today. You can do it manually, or you can use our platform, which is designed to do all of this work for you, along with other steps in the procurement process that we did not even scratch the surface on today, and to do all of that pretty much in a seamless fashion. If you haven't already, I encourage you to visit our site, register, submit a project, and see for yourself. So I think with that, we have entered the Q&A portion of the presentation. We have about 10 minutes left. And so I'm just going to start with some questions. I think this one might have been asked, and then continue to ask questions along the way if you have any more. So the first question that we have here is, the CapEx analysis requires several BOS and labor assumptions. How are you determining these, and do these change per region or per racking type?
Yeah, that's a good question. I feel like I'm going to miss a few details here, but this is absolutely correct. I'll start just with talking about location. So we do have a database of over 600 locations in the US that we have location modifiers for that affect both the assumed wage rates and the material costs. So whenever a project comes in, we get the project location, we'll find the closest location in our database that we have that information for, the location modifiers. And that's what we'll use for setting both our assumed labor wage rate and for the material cost. But there certainly are more details than that. If we're talking about racking, the costs that we use are based on many years of working with the various racking manufacturers and on quotes from those manufacturers. And we do have enough information so we have a good idea of how the racking costs change based on different site conditions, such as snow load and wind load. And so when we are computing a racking cost, it is based not just on how that rack interacts with that module, but how the rack interacts with that module based on the snow and wind loads. I guess the other thing I could talk about is for module installation costs. The time it takes to install a module is 100% affected by what racking you're using. And so we do have different assumed installation rates dependent on the rack. I'm probably leaving a few other areas off where we do account for this, but we absolutely are accounting for those things in our calculations.
I would say to add to that, yes, certain racks have certain kind of idiosyncratic impacts, right? Like, oh, this rack is very sensitive to this thing and this rack isn't. And so, our ability to perform a net present value analysis is not limitless in the way that we do it in a seamless fashion where someone puts a project in our platform and we give them this analysis within a few minutes. Clearly, we haven't stopped to understand exactly which rack they have in the topography and all of the rest. I think that largely we're putting people in the right direction. But if anybody's making a big decision, let's say you have a utility scale project, for example, it's probably wise for you to use the information we provide, maybe look at the top three options, and just double check that racking cost impact isn't one of those idiosyncratic situations where kind of things fall off the playbook, if you will. For full transparency and full accuracy, you'd want to just understand that. Okay, the next question I have for you, Tarn, is you mentioned performance models. Are you running PV-sys models for each option that when you do the analysis on a project for our customers?
So no, we're not. What we're working towards or working for at Anza is to provide, near instantaneous or certainly very fast results through our web app. PV-Sys at this point doesn't have any API or any clean way to run a series of models triggered by a web application. So to deal with that, we have built our own performance model. Right now, that model is in Excel, but we're about 3/4 of the way through building a model in Python that will be connecting to our app. And as we've worked through our performance models that we're building, what we know is that, PV-Sys is absolutely the standard. So each step of the way, as we built and are building the performance models, we're validating the results against PV-Sys to ensure that we get results that are very closely aligned with what you would get from PV-Sys if you were to run it.
How close?
So I would say that our models are within 1% of PV-Sys, and it very often it's less than that. Not all the time, but very often it's within 0.1% of what we're getting out of PV-Sys.
Thanks. All right. Remember, we still have a few more minutes. If you have any more questions, I'm going to go to the next one. What types of customers prefer using the IRR metric versus the NPV metric? Is it standard to offer both metrics in each customer engagement? So I'll take that one. I actually did a survey of some of our IPP customers and asked that question. And I think what I learned is that, first of all, they're both good metrics to use and largely are interchangeable. And you can't go too wrong using one versus the other, but they are not the same metric, and you can have a different result, like I'm going to choose this module versus that module by using one metric versus the other. It is possible. And one guidance I was given was for IRR, if you have a big constraint on your capital, I only have $20 million to deploy this year in solar projects versus a constraint on projects. So constraint on capital versus constraint on projects. In that case, the IRR metric may be more suitable for you because you're really trying to see how much, bang for your limited buck you can get. What return on that limited amount of capital can you get? Whereas, and this is the case with a lot of the IPPs that we deal with, and that as a developer over the last couple of decades we've worked with, often is the case. It's a shortage of projects to deploy capital on than the capital itself. Like, for all intents and purposes, the capital is unlimited, and in that case, it is more appropriate to use net present value, since you're ultimately trying to basically just maximize the bucket of free cash flow that you can ultimately quantify through the net present value metric.
And, I'll just chime in
Sure.
there. In the Anza app right now, we are doing our rankings based on NPV, and we have not so far heard a lot of feedback that customers are demanding or wanting IRR. But please, tell us if that is a metric that you would prefer to see, and we can work on building that into our application.
All right. I think maybe one or two more. What are some other factors that might influence the optimization levers in the revenue calculations? Maybe weather related or something.
Sure. Yeah. So one thing that we didn't spend much time, or really any time, talking about, which can be a lever, is the value of energy, or the PPA rate. The revenue deltas that we were talking about are very much, they're impacted by the performance deltas, or the yield deltas that we see between modules. But then really the value of those yield deltas are based on what the value of energy, or the PPA rate, is. So you could see module choices, the rankings of modules change depending on whether the value of energy was higher or lower. The other big lever in terms of maximizing NPV, that again we didn't talk about, and it's not something that we are currently doing through Anza, is system size. We found all of the tools that we're making available through Anza were born out of work that we did for our development company and optimizing those projects. And we basically found, when we're doing that work, module selection had a big impact, and then system size, right sizing the system, had a large impact on the NPV, or the value of the project.
All right, thank you. I think we've come to the conclusion of our webinar today. For anyone who was late, you'll get a copy of the recording sent to you automatically. So if you missed anything, you'll be able to catch up. And also just want to remind you that there are a lot of other aspects of the procurement process we didn't cover today. And then also remind you that we deal with storage as well in Anza, which is a topic we didn't cover today. But the same concepts will apply to storage in Anza over time as well. So thank you very much. Everyone have a great day.